So today we're going to dig into some of the drawbacks of each of these 5 methods. So we spent sort of like three days, I think, just learning how to do it, right? And we noted as we went, oh, this one seems fairer, this one seems easier. But we're going to spend a whole day now sort of looking at what's good and what's bad about the 5 methods now that we fully know how to do each of them. So one of the most basic ways that we judge the fairness of an apportionment method is by something called the quota rule. The quota rule says that an apportionment method should give each state no fewer than its lower quota and no more than its upper quota. So for example, if a state's standard quota, exact fair share, is 138.29, the only fair thing to do is give them 138 or 139 seats. You can't give them 0.29 of a seat, so the closest you can get is 138 or 139. If we gave fewer than 138, we call that a lower quota violation, and if you give more than 139, we call that an upper quota violation. All right, so think about Hamilton's method, the first method that we learned, where we give everyone their lower quota, and then we take any extras and we give them out one at a time, right? Can that ever violate the quota rule? Yes, how?
By giving larger states more seats.
Are they ever going to have more than their upper quota?
Yes.
Yeah? I don't know. So think about the method, right? Remember, we calculate standard quotas, then we round them all down. We chop off the decimals, round them all down. So everyone currently has their lower quota. Okay. And then you give some states one more seat, right? And if you add one to the lower quota, you get the upper quota. Is anyone going to get more than one extra seat? No. So Hamilton's method will never violate the quota rule. Everyone gets their lower quota. No one will ever get fewer than that. Some states will get one additional seat, which would give them their upper quota. And no one will get more than that. So we'll say everyone gets at least the lower quota, okay? Because that's how the method works. Everyone gets their lower quota. Then some states get one more seat, giving them the upper quota. Okay. So you can't have fewer than your lower, you can't get more than your upper, so this will never violate the quota rule. So that's a big pro for Hamilton's method, right? Never violates the quota rule. That's really good, because that is one of the most basic ways that we measure the fairness of a apportionment method. All right, so let's consider the quota rule in terms of Jefferson's method. This is a problem we solved last week. We apportioned this Congress of Parador example using Jefferson's method. So we got the standard quotas, rounded them all down, because that's what Jefferson's method does. And then when we added that up, it was only 246. So rather than giving out the forced surplus like Hamilton's method, we decided to change the divisor. We wanted all of our quotas to be a little bit bigger, right? All these quotas to get a little bit bigger, so that when we round them down, we get 250. So to make the answer to a division problem a little bit bigger, we want to make the divisor a little bit smaller. So we went to 49,500, calculated new quotas, round them all down, and that adds up to 250 perfectly. Nothing left over to fight about. But what do you notice about State B's standard quota and their final apportionment? Yeah. Right. So 138.72 is their standard quota. That's their exact fair share. Quota Rule says they should get 138 or 139. It's the only two fair possibilities, but we gave them 140. So this is an upper quota violation. Because we gave out more seats than the upper quota. And we noticed this when we first did this problem, if you remember. And it turns out that Jefferson's method not only produces these violations, but even worse, they consistently favor large states. Right? State B has the largest population, and they're the state that got that extra seat. So this is not good. And this problem came to light in 1832, one of the most heated apportionment debates in US history. Using Jefferson's method, New York standard quota was 38.59 seats. That's their exact fair share, right? So the quota rule says we should give them 38 or 39 seats, but they were apportioned 40 seats using Jefferson's method. And this was the last year that Jefferson's method was used because its constitutionality was questioned due to this upper quota violation. Adams and Webster's method were developed in response to this 1832 failure of Jefferson's method. But let's take a look at Adams' method. Using the Congress of Parador example that we solved last week. The final apportionment is down here at the bottom, exactly 250 seats. If we look at, again, State B's exact fair share versus how many they got, what's the problem? It's too low. Yeah, they should get 138 or 139, and we gave them 137. So now we have a lower quota violation. So it turns out that Adams' method can sometimes produce lower quota violations, but even worse, these violations consistently favor small states or penalize big states, whichever way you want to look at it. Right? So the state that got one seat too few here was the largest state. So they kind of got penalized in favor of giving seats to the smaller states. They lost a seat. So we can conclude that Adams' method is really no better or worse than Jefferson's. It's just different. It has a different built-in bias. And after considerable debate, the apportionment bill based on Adams' method never passed. And Adams' method was never used to apportion the House of Representatives. All right, so let's take a look at Webster's method. Again, we solved this problem together last week, so we won't have to take the time to actually calculate all these numbers. They're in your notes. Any violations of the quota rule in this problem? No. Everyone got either their lower quota or their upper quota. So state A, 32.92, they should get 32 or 33. They got 33, right? 138.72. They should get 138 or 139. They got 138. You can go through each of them, and they either got their lower quota or their upper quota. So we have no violations. So it turns out that Webster's method tends to produce apportionments that are pretty close to the standard quotas, right? So if your standard quota is 32.92, it tends to give you 32 or 33, a number close to your standard quota. But it does occasionally produce quota violations, both upper and lower. But these violations at least show no bias between large and small states. So it can, less frequently than Jefferson's and Adams' method, it does sometimes produce quota violations. They're both upper and lower, and it doesn't favor large or small states. So that seems like a good compromise between the two methods. But surprisingly, Webster's method was short-lived in the House of Representatives. It was replaced after 1931. Actually, I think this is 1941. sorry. It's replaced after 1941 with the method we currently use, Huntington Hill. And given how similar Huntington Hill is to Webster's, if you remember, Huntington Hill also sometimes rounds up and sometimes rounds down. It just uses a different cutoff than Webster's, right? Webster's always uses 0.5 as the cutoff. Above it, round up. Below it, round down. Huntington Hill's cutoff is kind of like this floating magical number that you have to calculate every time you want to round something. But the cutoff is generally close to 0.5, right? It might be like 0.49 or 0.496. So the cutoff is really close to 0.5, which means that these two methods are really, really, really similar to each other. Very, very close to each other. They tend to, in general, most of the time, give the exact same results, exact same apportionment. So it's not surprising that Huntington Hill's fairness is analyzed as very similar to Webster's fairness, because they are very similar methods. Again, Huntington Hill can occasionally produce quota violations, just like Webster's, both upper and lower, but it shows no bias between large and small states. All right, so it appears that Hamilton's method, of the 5 that we studied, is the only one that does not produce quota violations ever, right? Even though Webster's and Huntington Hill produces them rarely, which is good, Hamilton's never does. So that's a big plus for Hamilton's method. Why don't we just use Hamilton's method? How do you know that? Yeah, it does favor large states. It also has 3 other really serious drawbacks. And we're going to go through an example to demonstrate each of these. So we have the small country of Calavos. It has 3 states, Bama, Tecos, and Illinois. Total population of 20,000 and 200 seats in the House of Representatives. Determine the apportionment of the 200 seats under Hamilton's method. Take 5 minutes or so and calculate the apportionment for this country. Okay, so let's quickly go over this. The first thing we have to get is a standard divisor. I usually just do this calculation off to the side somewhere. Total population divided by total seats is 100. This is your standard divisor. It's called the standard divisor because you use it to divide every state's population. Oh, thank you. Yeah. So now I take each state's population and divide by the standard divisor. So often we write in here what you're dividing by if you want to have it like in your table. So I can put it right there. So dividing by 100, that's easy. I like that. So we have 9.4, 90.3, 100.3. If I did everything right, that should add up to exactly 200 seats. Then Hamilton's method gives everyone their lower quota, chops off the decimals. So you have 9, 90, 100, which adds up to 199. I have 1 more seat left to give out. Who should get it? Bama. Yeah. Why? They have the largest decimal. And if I had more extra seats to give out, I would give them to the next highest decimal, etc. Okay, so luckily I only have 1 seat to give out because these 2 tie and I wouldn't know what to do. I don't know. So I have 10, 90, 100, and that will add up to exactly 200. Okay, all done. All right, so 10, 90, 100. Keep that in mind. Move on to the next one. Overnight, the number of seats increased to 201 instead of 200. So now I have more things to give out. I have more seats. So the states are like, ooh, who's going to get the extra seat, right? They're all excited. Maybe we'll get it, right? So recalculate the whole thing using 201 instead of 200. Let's see who gets the extra seat. Okay, so let's see what happens. I get a new standard divisor where I take my 20,000 people and divide by 201 seats. And that comes out to like 99.5 with some other decimals, but that's good enough. All right, so now I'm going to divide each state's population by my new standard divisor of 99.5. And I think I get 9.45, 90.76, and 100.8. Good. All right, so if I add those up, I should get something really, really close to 201. It might not come out to exactly 201 because each of these decimal pieces we rounded a little bit, but it should be really close. So next step in Hamilton's method is round everything down, chop off the decimals, and that adds up to 199, which means I still have how many seats left to give out? 2. Who gets them? Tekos and Ilnos. So we have 91, 101, and 9 to get 201. So what are your thoughts? What do you think of the results here? Why? The larger states benefited, yeah.
That's not true all the time. It's just whoever has the best.
Yeah, whoever has the largest decimal. But so who's really upset? Bama, right? When there were 200 seats to give out, Bama got 10. And now we have more seats. Now there's 201 seats. And all the states were like, ooh, who's going to get the extra seat? Right? And we ended up giving one of the extras to Tekos. We'll just say we gave the extra to Tekos. Then we took the other one from Bama and gave it to Ilnos. So Bama lost a seat. Right? So the result we've just seen is called the Alabama paradox. It happens when an increase in the number of seats to be apportioned causes a state to lose a seat. The name comes from the 1882 apportionment of the House of Representatives, and here's a summary of what was being debated. Alabama, Texas, and Illinois, with 299 seats. Alabama got 8, Texas got 9, and Illinois got 18. When we increased to 300 seats, Alabama got 7, Texas got 10, and Illinois got 19. So Alabama lost a seat, even though there was an extra seat now to give out. Yeah, 1/100th. No, 1/1000th. That's the thousandths place. So this is something also that the House of Representatives was constantly changing how many representatives it had in it historically. Now it's fixed at 435, but constantly we were not only apportioning what method should we use, but how many seats should we have. So this was a big paradox that came to light in 1882. Okay. Okay, so that's one big drawback, the Alabama paradox. Here's an example that will give us another paradox. In the year 2525, the 5 planets in the Utopia galaxy finally signed a peace treaty and agreed to form an intergalactic federation governed by an intergalactic Congress with 50 seats. So this is the story of the 2 apportionments that broke up the Federation. Yeah, this is not an accurate historical example. This is made up. All right, so I want you to do 2 things. First, calculate the apportionment in 2525, get the final apportionment. Then go on after 10 years, and we did a census, and the population's changed a little bit. So I want you to reapportion those 50 seats according to the new populations. So go ahead and do both of those problems and then compare. Okay, so why don't you guys just tell me your results for the apportionment in the year 25-25? Final apportionment. 8, 4, 10, 11, 17, adds up to 50, right? Okay, if you didn't get that, check with the neighbor or I'll come around in the next problem and help you, okay? 8, 4, 10, 11, 17, 50. All right, so let's, when we redo the apportionment, because the populations have changed a little bit, and this is what we do, you know, every 10 years we have a census and we reapportion things, make sure everything is still fair. Okay, so what is the final apportionment with the new populations? It's the same thing, so 8, 4, 10, 11. Okay, so we got some controversies going on here, so let's calculate it together. So my new standard divisor, I'm going to get by taking my new total population and dividing by 50, and it comes out to what? 18.18. Okay. So then you divide each population by 18.18. Open up a calculator. Okay, so 150 divided by 18.18 is 8.25. 78 divided by 18.18, 4.29. 181, 9.96. 11.22. 16.28. Okay, so then we do lower quotas, we run them all down, we get 8, 4, 9, 11, 16, and when you add those up, you get 49, 48. 12 plus 9 is 21, 32, 48. Okay, so I have two seats left to give out. Who should get them? Coney and Beta. 0.29 is the biggest. So this is going to be 10, this is going to be 5. Everyone else stays the same. Okay, so remember our previous apportionment was 8, 4, 10, 11, 17. Okay. 8, 4, 10, 11, 17. This was the previous. All right, what are your thoughts? Elysium's population went up. They have more people than they used to, right? 295 to 296, but they, oh no, they gained a seat. Oh no, they started with 17 and now they have 16, yeah. So they lost a seat. So if a population goes up, the worst that should happen is you stay the same, right? If anything changes, you should gain an extra seat to have a representative for those new people who live in your galaxy or whatever. Right, so this is what we call the population paradox. It happens when a state's population goes up, but the number of seats it's apportioned goes down. Okay, so that is a big problem, right? That sometimes a state's population can go up and it loses a seat. All right, one more big drawback for Hamilton's method. Change of pace, we're going to use a non-political apportionment problem. So we have a garbage company. It serves Northtown and Southtown. Number of homes in each town is listed, and it has 100 garbage trucks. How many trucks should it send to Northtown, and how many trucks should it send to Southtown? Yeah. All right, go ahead. Use Hamilton's method to figure out how many trucks it should send to each town. All right, so why don't you guys tell me, what's the final apportionment when you have just Northtown and Southtown and 100 trucks? 10 and 90. And that gives us our total of 100 trucks. So send 10 trucks to Northtown, 90 trucks to Southtown. Using Hamilton's method, that's how we can split it up. All right, and then the garbage company gets hired by Easttown, another town with 5,250 homes. To accommodate this town, they buy 5 new trucks, right? Because they don't want to affect the service to Northtown and Southtown. So they buy 5 new trucks to service. It did, I know, right? So when you carry out Hamilton's method with the additional town and 5 additional trucks, you end up giving Northtown 11, Southtown 89, and Easttown 5 trucks. So they bought the 5 new trucks to accommodate Easttown, right? So all 5 new trucks are going to go to Easttown, but then it just seems completely random that instead of doing 10 and 9, sticking with the 10 and 90, they switched it to 11 and 89. So this is another paradox that happens when we use Hamilton's method sometimes. The addition of a state can affect the apportionment of other states, right? It's called the new states paradox. The addition of a new state with its fair share of seats can affect the apportionment of other states. All right, so here's just a quick chapter summary. We've got our 5 methods. Hamilton's is the only one that does not violate the quota rule, but it had these 3 weird paradoxes: Alabama paradox, population paradox, and new states paradox. And it favors large states. Jefferson's method and Adams' method both produce quota violations. Jefferson's method upper only, Adams' method lower only, and Jefferson's favors large states and Adams favors small states. Webster's method is the one where you round conventionally, and Huntington Hill, you round almost conventionally using the geometric mean. And both of these can occasionally produce both upper and lower quota violations, but they're neutral. So it turns out that any apportionment method that does not violate the quota rule will produce paradoxes. And any paradox-free method will violate the quota rule. So it is impossible to have a perfectly fair method, and this fact is called Belinsky and Young's impossibility theorem. Reminds me of the voting impossibility theorem. Yeah. So there are no perfect solutions to the problem of apportionment, but some of these are better than others, right? Because we prefer neutrality over, well, unless you're from a big state or a small state.
So there's no real changes in the Webster and the Huntington. Why did they even bother changing it?
Good question. So Webster's method and Huntington Hill are really, really similar methods. They hardly ever produce apportionments that are different from each other. Why did they bother changing it? So Congress was using Webster's method, and they were constantly fighting over changing the method. Someone was always proposing a new method, and they were voting and fighting, adopting a new one, throwing it away, adopting a new one, throwing it away, because states were felt like they were not getting a fair deal, or they were trying to get a better deal for their state. So Congress hired a panel of mathematicians, right? They're already using Webster's method. So the mathematicians sit down and try to brainstorm. They look at all the methods that have been used, try to come up with a new method. And imagine you're on this panel of mathematicians and you say, you know, the method they're using is actually fine. And can you imagine they're like, we can't go back and tell them that they're doing it right. We're mathematicians. They're politicians. We have to come up with something better. So they came up with something that looked a lot more complicated, but was really the same.
I like it.
Mm-hmm. So they had to justify the money they made, right? Yeah. Mm-hmm. Okay, so I just want to share with you my mnemonics to remember what the 5 methods are. Hamilton's method is like a holiday when you have ham, there's always extra ham to give away at the end of the day, right? You have to give away the surplus seats like you give away ham at the end of the holiday meal. All right, Jefferson's method. The J looks like an arrow pointing down, so you round everything down, and the standard divisor will go down. The divisor will be less than the standard divisor. Adams' method, the A looks like an arrow pointing up, so you round up, and the divisor will be bigger than the standard divisor. Webster's method, that W, it points both up and down, so that indicates round conventionally, sometimes up, sometimes down. And you can't tell which way the standard divisor is going to move, right? You just have to use the rule. And then Huntington Hill, what the Hill kind of rounding rule is that? Yes.
I have a question about that one.
Sure.
When we're comparing so initially you get your standard, whatever, you get your decimal, and then you add the two, whatever.
The lower and the upper.
Right.
Yeah, you multiply them in square root.
Yes. That's true.
Yeah.
And then you get a new decimal.
Yes. That's your new cutoff.
That's it, right.
Yeah.
But then you compare the two in order to get your the number you found. Which one are you seeing? So when you're doing the comparison, it's where I get confused with the rounding.
Okay.
Compare the new
So-
number to the old one as far as
So the new number is acts like the 0.5 used to act in your standard rounding. So like say you have 32 and 33, right? You multiply them, square root, I think you get 32.496, right? So instead of using 32.5 as your cutoff, if your quota is above it, round up, and below it, round down, now you use 0.496 as your cutoff. So let's I'm going to draw a number line, and this, yeah. So let's say we've got a 32 and a 33. And we'll say the standard quota is 32.68. Okay. All right, so my geometric mean, which is my new cutoff, let's just double check that I'm remembering this correctly. 32 times 33, and then square root it. It's 32.496, which is really close to 0.5, right? 32.5. And this is how because it is very easy to forget like which one is the one you're comparing, right? Which one is the cutoff and which one is the one getting rounded. Okay. So this is the number I'm trying to round. Should I go up or should I go down? This is my cutoff, right? So normally in standard rounding, I would use 32.5 as my cutoff. And this is how I remember is like this is very close to 32.5. So this is the number that's the cutoff. If this number is above it, you round up, and below it, you round down. So we put this number on my number line, 32.496. This is my cutoff, right? And then you take your standard quota, 32.68. It's above the cutoff, so you round up. So 32.68 rounds to 33.
create a new number. Let's say if we didn't get all the seats we make that new number, right?
Right.
And then we have to recompare. This is where I get confused. The second comparison.
Okay. So we get a modified quota. Right. So let's say we have a modified quota of 32.42, something like that. Now, your geometric mean is going to be the same because your lower quota and your upper quota are still 32 and 33. So that you're going to compare to that same number, 32.496. Right. Now you'd round down. 32.42 is below your cutoff, so you'd round this down to 32. Okay. All right, so I have some group work for you to work on, and I will come around and help with any confusions that remain.